Hi everyone, in this video series we're going to explore electric fields in a practical way. We'll talk about the theory, but more importantly, we'll actually see how they behave through real experiments. To do that, we need a reliable and reasonably powerful high voltage source. And for this project, we're going to reuse parts from an old CRT monitor. The board you see here comes from a Samsung SyncMaster 17-inch monitor. This section contains the flyback transformer, the component that originally generated the high voltage for the CRT tube. We're going to use this flyback transformer as our high voltage source. Next to it, we have two important diodes. One is a clamp diode, the other is a fast recovery flyback diode. In our new circuit, we'll use both of them to control the return energy and to protect the switching device. Here we also have the switching MOSFET, which we'll use to drive the primary winding of the transformer. Looking at the schematic, pins 1 and 2 are the primary winding, and pin number 8 is one of the high voltage output terminals. Even without the schematic, we could identify the primary winding using a multimeter. Usually the primary has the lowest DC resistance, just a few tenths of an ohm. To find the negative terminal of the high voltage output, we can use a low current power supply, for example 24 volts. Connect the negative terminal of the 24 volt supply to the negative probe of the voltmeter. Then connect the positive probe of the voltmeter to the high voltage output wire. Now apply the positive 24 volts to different transformer pins, one by one, until you see a voltage change on the meter. Because of the internal diode chain inside the flyback, you'll typically measure a voltage drop of around 18 to 22 volts. The model of this transformer is FQM19A005. It has built-in high voltage diodes, so the output is rectified pulse DC. For the experiments we'll perform later, we need an adjustable high voltage output. That's why we'll drive the transformer using PWM. By changing the pulse width, we control the energy transferred in each cycle, and that controls the output voltage. For precise control of frequency and duty cycle, I'm using a function generator. But if you don't have one, you can easily drive the MOSFET using a simple oscillator circuit. For example, one based on the NE555 timer. Our circuit for driving the transformer, based on the monitor schematic, uses a single transistor design. The monitor operates at around 60 kHz with 80 volts. But to drive the transformer at a lower voltage, we use a frequency of 16 kHz with a 40% duty cycle. The primary current must be controlled to prevent transformer core from saturating. When high voltage is generated, a strong electric field forms between the tip of the electrode and the surrounding air. This field ionizes the air and creates plasma. When the field strength is sufficient, you observe the first phenomenon, corona discharge. A few very important notes. Even after power off, the output capacitors may remain charged. Do not bring your hand close. The current must be limited. Use proper discharge resistors and insulation, Maintain a safe distance to prevent shock or injury. This is the first corona effect. Notice the faint purple glow and the low current. This is the initial stage of discharge, and later we will move on to a streamer and arc. In the next part, we'll explore more interesting phenomena such as a streamer and arc, and perform various high voltage experiments. Make sure to stay tuned.